Hello everyone. I hope everyone is fine and the symposium was great for everyone. Today, my mentee Turan Ocak from Bursa Technical University will talk about coding theory. He want to give an overview of coding theory, and he will tell us a relation of two specific code families: Reed-Muller, the binary Reed-Muller codes, and the Hamming codes with dual codes. So now, Turan, you can start.
Hi everyone. Uh, Today I'm going to talk about coding theory, and I'm start now. Here's the flow of my speech. I start with introduction to coding theory and some definitions. After that, I'll talk about dual codes and parity-check methods. And after that, I give the binary Reed-Muller and Hamming code, and we find the exact Hamming code with using Hamming code. And after that, I give exact Hamming code and Reed-Muller code relation. Let's start with definition of code. A code tree is basically subset of A to the N, and where is then elements of code are called code words, and length of n is n. I give the now definition of the linear code. Linear code is important for us because it has a lot of advantages. Linear code is basically subset of a vector space. Here's an example about it. Let's alphabet B and 0, 1, and the code is here in linear code, and elements are code words. Now I'm going to talk about main parameters. Length of the code and dimension and minimum distance are our main parameters. Dimension about is measure efficiency, and minimum distance is about measure reliability. I talk about minimum distance, but I gave now definition of the Hamming distance. Let's take two code word x and y, and the different entries of x and y, number of the different entries x and y is called Hamming distance, and different entries not equal to entries equal 0 is Hamming weight function. In linear code, the minimum distance and Hamming minimum distance is same as minimum weight. Now I give some example about it. Here's our code family. Our length is 4 because we have 4 entries. We have 4 entries because of that our length is 4. We have two code words, but one of the code words are basis element. So our basis either dimension is equal 1 and minimum distance is equal to 2 because two elements are different. I have another example about it. Here's our code set. When we look for each code word to find minimum distance, there are 4 entries different. There are three and etc. And minimum distance is equal 1 because the minimum. For the linear code, minimum distance is same as the minimum weight. Now here's a Shannon's model. Shannon is a mathematician and who starts coding theory in 1948. Here's a model. We have a message search and we try to find error and correct errors. And this model is about it. Now I'm going to talk about main problem of coding theory. We try to optimization to or all parameters like n, k, and minimum distance. When n is smaller, we can faster transmission can occur. When n is fixed, and measure of efficiency of the code minimum distance indicates error correcting potential. When minimum distance is higher, we can make more errors. We can make more errors correct. Now I give theorem about it. A code C detects U errors if and only if minimum distance is higher than equal to U. A code C corrects V errors if and only if minimum distance C is higher than equal to 2V plus 1. If C is a minimum distance, it corrects minimum distance minus 1 over 2 errors. Now I give the theorem singleton bound. It gives us a relation about the parameters. Minimum distance is less than equal to n minus k plus 1. Now I give definition about MDS codes. MDS codes basically satisfy the singleton bound, where k equals n minus d min plus 1. We call this code maximum distance. Here's an example about it. Now I give generator matrix. Generator matrix is basically basis whose rows form a basis element of matrix. And we have code here and two codes. Our length is n and k is 2. We have two elements in our bases, 0, 1, 1 and 1, 0, 1. Here's our generator matrix. Now I talk about dual code. Let's see subset of FQ to then be a linear code. It doesn't necessarily be a linear code. We can find any code for dual code, but I take definition here linear. A in FQ to the n, A times C equals to 0 for any A in C. There is some proposition for linear code, dual codes. When we take dual of the dual code and equals to dual code, when we look at dimension dual code is equals length minus dimension C. A parity-check matrix is a linear code, dual code of generator matrix. Here's the standard form of generator matrix, and here's the standard form of parity-check matrix, as you saw. We have theorem here, and we want to find parity-check matrix. If G is the standard form of generator matrix, and we find the parity-check matrices, minus X transpose, so identity matrix and name is K. Now I have example about it to find parity-check matrix. Here is our generator matrix, and we have 10 columns. Our length is n. First, we need to take the G standard form. Because of that, we arrange columns 1, 4, 5, 7, 9, and 9. We permutate the columns. We take G prime matrix. Here's the first part of identity matrix, and second part is the X matrix. We have to find minus X is the transpose matrix. And we found this matrix, but we work at F3. So because of that, minus 2 is equivalent to 1 and not 3, and minus 1 is equivalent to 2 and not 3. And here's our minus X to transpose matrix. Let's call H prime to this matrix, and we have to arrange back the columns when we find this parity-check matrix of this C. Now I give definition Reed-Muller code, binary Reed-Muller code. Binary Reed-Muller code is a family of code, and it is important. Reed-Muller codes of first degree denoted by Rm, and binary linear codes for m higher than 1 as follows. This set, F2 to the 2 set. And we have a recurrence inversion here. That's m higher than equal to 1 and R1, m plus 1. We define the set this way. Here is the U notation used for bitwise complement. Let's make an example about what is bitwise complement. Let's take U 0, 1, 1, 0, and the bitwise operator is 1, 0, 0. It inverts all bits. Now I give proposition for generator matrix for Reed-Muller, binary Reed-Muller code. For R equal 1, our generator matrix is 1, 1, 0, 1. Basically, we solve set here R1, 1, and we have two elements in bases. And these are 1, 1, and 1, 0. This is our generator matrix. So we have a relation like that. Now I give hemicode. Hemicode is a let R equal to and C be a linear code with length 2 to the R minus 1, whose parity-check matrix is such that columns are all of non-zero vectors and F2 to the R. We call the C is a binary hemicode, and we denote it by hemic R2. Now I give example about hemic R2, parity-check matrix of hemic R2, but R is equal to 3. Now I give extended hemicode. The extended hemicode is obtained by preceding each code word with a parity bit and is linear. 2 to the R is n, and 2 to the R minus 1 minus R is k, and 4 is the R minimum distance. We denote this code extended hemicode. The parity-check matrix of extended hemicode is constructed by taking parity-check matrix of the hemic R2, adding column of all zeros and adding rows all of ones. Now we have proposition. For every R is more than equal to 1, the extended hemicode is dual code of Reed-Muller 1R. Binary Reed-Muller code. I give some ideas for proof. Let R equal 1, and here is the F2 1 set. R length is 1. So we wrote all matrix except non-zero matrix. Here is the R first matrix as 1. When we add the column 0 and when we add the rows 1, we get hemic extended 1 matrix, and we make some row operations. We can see G is equal to R11. For R equal to, we can say R set is here, and we brought all code words, non-zero code words in the columns, rows. We get this matrix. We want to find extended hemic matrix. So when we add the 0 on the columns and add the 1 rows, We got hemming exempted too. And the generator matrices are 1, 2, as denoted for column GM and zeros and 1, 1. Here's our G matrix. You make some row operations. Also, we can see this equivalent, and we can make this for R equal to and find this matrices. We can see these are row equivalent to. And all of them gives us an idea about proof. We can use induction method for can of the proposition. Thanks for your attention.